Okay, let's have a look on last week's lecture. Okay, so I think we can start it around here. Okay, so it's basically that in absorption, what we would like to do is to just wait. Okay, yeah. Uh, what we would like to do is to determine the height of the absorption column, right? And then how much is the height of the absorption column, and then we can start with this differential mass balance, where from the bottom here we have GS for the inert, yeah, the superficial inert gas flow, right, with the composition, or sorry, with the mole ratio of Y, and then some of them is being transferred into the liquid, and the amount of the transfer into the liquid is called Na multiplied with A. Na is the mass flux. Mass flux means, molar flux. Molar flux means the amount, the rate, or the amount of the molar transfer of the solute here goes into the liquid. And flux means that it is divided by the area. Okay, so in order to find the rate of the mass, or the molar of a of the components that being transferred into the liquid, we have to calculate with A, which is A is should be the this A should be the area, yeah, the area, which, okay, so the A should be the all area, and the area in this differential boundary is actually the A, or the wetted area of every packing, multiply with the volume, which is dV. Okay, and then G so make it I'm gonna make it bigger like this. Okay, so GS dash multiply with the Y, with the mole ratio, the input is actually is the output. The output is the NAA, yeah, and another one is Y plus dy. So the Y plus dy is the mole ratio at the height of Z equal to Z plus dZ. Okay, and by rearrange the equation, we found that this one dV is equal to minus GS dash divided by KYA multiply with dy over Y minus Yi. Okay, so in summary here, if we do the integration, okay, so if we do the integration here, okay, it's called that integration of dz from z equal to 0 to z equal to h. Okay, so to find the height, the overall height from equal to 0 to equal to h, that's actually actual to the integral from y1 to y2 from the bottom here, the y1 to 1 2 negative. Why negative? Because the y is actually decreasing, yeah, the y1 is the higher one, the input gas that contains many solute that we want to remove, and we have the clean gas here, so this is negative. And then this one, yeah, and then gs dash divided by kya multiply with dy over y minus yi. Okay, so again, here we maybe just to remember from last week's, we know the y1, we know the composition or the mole ratio of the gas in the input from the problem. because usually in the problem they will state it. Yeah, the problem will be stated that okay, so this is the composition that the gas that would be treated. Okay, and the second one, Y2, is actually the target. What is the target of the clean gas that we would like to get? So we should know this one as well. So we know Y1 and Y2. And the gas also should be given because it can be treated how many, so how much is the gas that should be treated. And chi Ya, if the K is small, that is called mass transfer coefficient in gas phase. Yeah, Ya. Because sometimes, we also can change this one with X from the liquid side, but of course when we construct the absorber column, we want to know this is the requirement that we need, yeah, that we know the gas input, and also we want to know the target or the gas mole ratio output. So this is the mass transfer of gas in a phase, and multiply with A is the wetted area, yeah, the wetted area or the contact of the area in the packing. And usually in the commercial one, or that if we want to calculate something, yeah, we want to calculate, usually it form in the KWI is specific for each packing. Okay, this is not thermodynamic data, this is a mass transfer data, so this is should be based on experiment, and then usually the experiment is done by the vendor, and then the vendor will give you the range of KYA for each packing, and then yeah, this is made from the vendor. Okay, so now the problem now is to how to calculate this one, because this is a variable, y is a variable, while yi is the composition in the equilibrium, right? If you remember, y is the composition, or sorry, the mole ratio in the bulk phase, in the gas phase, the bulk gas phase, while the yi is the gas composition in the interface. Okay, now so just that's a little bit of review from last week's lecture, and then let's have a look how we try to solve this one in the next chapter, or not in the next video. Okay, need to maybe stop sharing and then find in the next one. Okay, let's have a look about this formula. This is the formula to determine the height, and the height is actually usually we call these sides, the GS dash divided by KYA, is called HTU, or we call it height of transfer unit in a gas phase, or we call it HTG. Yeah, so this one is the height of the transfer unit, and it's multiplied with those integrals, and the integral from y1 to y2 this is to remove the negative. We do the integral from y2 to y1. Yeah, this is to remove the negative, equal to dy divided by y minus yi, which is in the interface, in the equilibrium run. And then this one is called the number of transfer unit. Okay, what this tell you, this is very important, because this is the the one that we can manipulate if we want to find the height. Let's say if you so for example, if you want to let's say if you want to increase the, this is y2 to y1, yeah. If you want to increase the purity, let's say the purity of y2, let's say, so if the NTU is increasing, the number of transference units increasing, that the height would be also increasing too, yeah, because if you increase this one, and the height also would be increasing too. Okay, and another one, if you have a good transfer of the KYA, yeah, the height transfer unit, if you have a good transfer, for example, if you have a good transfer in the gas phase, for example, you have a good packing, you have an expensive packing, yeah, you have an expensive packing, which is you have a KYA, a high KYA, yeah, maybe with a good contact with liquid and the gas, and also the contact of the mass transfer is also good, then the amount of KYA is gonna be increasing. Then the HTU, the height transfer unit, is gonna be making lower. Okay, so then your height also would be lower as well. So then you're gonna need less packing, and you're gonna need less height, then you're gonna need capital costs. Okay, so again, it is a drawback, and also there is a not a drawback. This is a trade-off between if you want to have a good packing, maybe I think the cost would be more expensive, yeah, compared the maybe it's not so efficient packing, but it's gonna be resulted in your HTU is gonna be lower, yeah, and then for a certain composition or the certain NTU, similar NTU, then you will need less height. Okay, right. Okay, so so that is the formula about the height, and you also can read it on the liquid phase. In the liquid phase, if you want to check so that means in the absorber column you need to check your liquid in, yeah, and also you need to check the liquid out, and then you need to get the samples and then put into analyzer and then into the lab and then check the composition. But it is not so efficient compared to the gas, because in a gas here we have a more advanced analytical tools to check the composition. For example, using gas analyzer, so it can be online at any time. Yeah, so we can find our Y1 and Y2, right, compared to X2 and X1. So, and then it's very rarely that the people looking at from the X, especially if the solvent is really expensive, and then it's the process is targeted to really recycle the solvent. Maybe they would like to look at this one, but usually they always use from the gas phase. Yeah, if you look at from the from the liquid phase, then you want to find this one is from LS dash, from the flow rate of your liquid in a superficial, and also from KXA. Small k, that means a mass coefficients in liquid phase. Yeah, X means it's in the liquid phase, and A again is the wetted area the wetted area of the packing. Okay, why I say this is small k, because later on we're gonna talk about mass coefficient of overall, yeah, later on. Okay, up to here, any question? I think you should have any questions. You should have questions now, or please let me know if you want me to repeat the explanation. Anyone? Any questions? Not yet? Okay, let's just continue. Now, the problem is, I think I also talked about it last week. What is the correlation, hubungan antara, the correlation between y and yi? Okay, so let's have a look here. This one again, yeah. Because here that would be okay. Because here we can calculate the HTU, but we don't know how to calculate the NTU, yeah. Because there is y and yi, okay. And then let's look at the graph. Okay, what is this black line here? Anyone?
The equilibrium line.
Huh?
Equilibrium line.
Nope. The black one.
Operating line.
Yeah, that's good. So which one is the equilibrium line, Kevin?
The red one ya Bu, yang
Yeah.
1, 2.
Yeah, that's right. So this is the red one, yeah, the equilibrium. Okay. So let's use another color here. Yeah. Okay. Let's say I have these points, and if I read it here, it becomes the y. Okay. So this is y. Okay. It should have correlation with the x, with the y at equilibrium in this one there. Okay, we don't know what is the correlation with the equilibrium. Let's say using a graph, using this line. Yeah, let's say this line is the correlation of y and yi. Okay, so if this is y, how to read yi? Can you know? Do you know where to read yi? Yi is the mole ratio at the interface. Yeah, and from the bulk phase to the interface there is a mass transfer. Okay, so if I said that, let's say this line is the correlation between y and yi, so I would say, for example, in this point, this is the equilibrium one, so I'm gonna go that way and then read my yi here. Yeah. Okay, so let's put it, this one is y. Okay, so the correlation is y to yi is stated by the mass transfer, because in a gas phase, from the previous one, this is the mass transfer equation. The Na multiplied with A, the mass transfer flux multiplied with all the area, equal to the coefficient of mass transfer, and then multiply with the delta. The delta is the differential, the driving force. Yeah, the driving force is this one. If you have higher y to yi, then you have a high mass transfer. Okay, and then multiply with dv. Okay, in another way, from here the y will have a correlation with x, the yi will have correlation with x because it is equilibrium. So in this point, I can read that if I have this yi as the equilibrium, I can read into the x here, and this is my xi. So I can read my xi. Okay. Now, and then if this is the xi, so over x here, the correlation between capital Y and capital X here is actually the operating line. So this is your x. Okay. So the correlation between the I in the interface to the the X in the interface to the X in the bulk phase is also can be written with the mass transfer. And when steady, the rate of transfer from the gas, the component, the solute from the gas to the interface, it should be similar to the rate of transfer of the composition of the solute now in the liquid from the equilibrium or the interface into the bulk phase. Okay, so when steady, NaA should be the same. Yeah, even in the gas, it should be the same with the liquid. So with that, okay, because the transfer in the gas phase and also it should be similar with the liquid, then we can say the green one here is equal to the blue one here. Okay, so because it's the same, so we can rearrange. This is chi YA multiply with the differential, the delta between y2 y1 dz equal to chi xa multiply with xi minus x dz. Okay, this can be cancelled out, and then we can just rearrange this one, ki kx over here, kya over here. Why we don't cancel out this one? Because usually in the vendor they always written as chi xa or chi ya, yeah, so then we don't need to cancel out the a over here. This is like one package. Okay, and this one become y minus yi, and then this one divided by xi minus x. Okay, so this is number one. Okay, now let's have a look over here again about the graph. Then here, that's the good thing about the engineering, yeah. They try to find tricks or something. They want to try to find solution. So here, if you know about gradient is defined as delta y divided by delta x. Yeah, what is the delta y? The higher minus lower one, y minus y1. Yeah, the delta x equal to xi divided by x. Okay, so this is very similar with this one. Okay, so then if we want to make it as a slope, equal to y minus yi, and if we can say that one, we can put it minus in here, and equal to x minus xi. Okay, so because so that's why, because the gradient is actually chi xa divided by chi ya. Now if we just to put everything over here, we can say that the slope is actually the minus, yeah, so this is the, so this should be negative, yeah, it should be, yeah, sorry, just, oh, this is from xi to x, yeah, this is to xi to x, right. Wait, this is xi to x, yeah, that should be the negative one there. Okay, so here we found that the slope is actually minus kxa divided by minus kyi. So that tells you that if you have the mass transfer coefficient in a gas phase, and also you know the mass transfer coefficient in a liquid phase, then you can find the slope, and to get the slope is just enough to find your y. Okay, so but I don't understand, but why we have to find the slope? Now here's the things. Yeah, in chemical engineering or in any engineering things, if we can't find sorry, which one? If we can't find solution with analytical, we can find using approximate, yeah, perkiraan, or using numerical. Okay, that's why we have course analytical mathematics matek ya, and also computasi process, because we want to be able to calculate even with the analytical one and also the approximation if we can't solve it with analytical one, right? Okay, now here because the second one, the NTU, is integral of 1 minus y dy divided by y minus yi. So because it is difficult to find the integration, yeah, to find the integration here, so we can so let's solve it using approximation. Have you ever heard about Trapezium Rule? Who knows about Trapezium Rule or Simpson's Rule? Anyone? Have you heard about that?
Maybe just the trapezium rule. The trapezium rule. Yeah.
Okay, so in Trapezium Rule, if you have a graph like this, okay, and then we don't know how to do it, we can change it into, for example, from y, yeah. So we can make it we can maybe divide it into 4, for example, yeah, and then we calculate the area of number 1, number 2, number 3, number 4, and then we sum it up, yeah, the trapezium, which is the trapezium is actually the half of your for example this one, yeah, y1 to y2, yeah, y1 plus y2 multiply with the this plus this divide by 2 multiply with the delta x. I think that's that one there, yeah, the trapezium. Okay, so with that one too, we can also try to find or to divide the calculation, the graph using Trapezium Rule. Okay, so because this one is actually, we also can write it as integral of 1 over y minus yi dy. Okay, so this one is the function and this is dy. Okay, so how if we calculate this one for each the segment and then multiply with the delta and then we integral? But maybe you're gonna say but how about the error? Yeah, that's the thing, yeah. Of course if you do the approximation of, if you do the numerical thing, of course it's not gonna be exact, yeah, it's not exact, but it is better compared to we can't solve it anything. Give me 1 second. So what we need to do here is how if we divide the slope and also divide the graph, divide the area here into some segment. Let's say we want to increase from y, so I'm gonna write here, for example, from here, from y1 to y2, okay, from this one into this one, okay, and then let's make this one into a segment 1 2 3 4 5 6 7. So I need to divide these numbers into a similar one. So usually you have to find your number from y1 minus y2 and divide the 7. Sorry, the segment is 1 2 3 4 5 6, yeah, divide by 6 segment, and then you will have your delta y, okay, and then you can write it here up to here, for example y1 or y, and then for example this is for example from 0.9 to 0.1, that's just an example, yeah, 0.09 to 0.01, for example, and then this is the segment, so you can write your y over here. Okay, and then once you know your y, y1, yeah, y, the capital Y, you can find the yi. How do you find the yi? How to find the yi? How to find the yi? Using the graph, yeah, using the graph in this one here. Okay, if you have a number of y, you have to calculate the slope from the minus kxi and divide by kyi there, then you will find the yi. Okay, you will find the y equilibrium. So if you have the y, the number of y, using the graph you can find the yi. That's why later on in the exam later you will need to use millimeter block. Yeah, you will need to use the graph, the millimeter block. So you first you should draw the you should draw the x, y, and y. Yeah, so this is gonna be your x and this is gonna be your y, and then from the problem you should draw the operating line, and then you also plot your equilibrium line, for example, and then you check which one is your y2 and y1, yeah, and then check the problem if they have the chi xa and also chi ya, and then you can find the slope, and then let's say the slope is minus half, for example, yeah, the slope is minus half, and then you can using the graph you can find the millimeter block and then find the minus half and then try to find it, okay, and then you can get your y1. Okay, later on we should be able maybe tomorrow we can be discussed with an example, so how to do it in a graph. Okay, so then you can get your number for yi, yeah, for the y equilibrium, and then you can also, because the function is this one, yeah, 1 divided by y minus yi, then you can find the number. Okay, you can find the number and then you do it for 6, yeah, and then you can add it, and then you can get the this one, yeah, you can get the area. So the area is actually the summation of your trapezium. Okay, Bob, I want to use maybe square method or not square method, yeah, or like a Simpson's rule or something, yeah, if you want you can, but trapezium is a good idea, a good approximation as well. We have still a little bit of error in here, but that's fine. So then we get the NTU. So when we got the NTU, then we can just multiply with the HTU, and then there you have it. You have the height for your absorption. Right? Okay. Up to here. Questions or should I repeat which part? No? Okay, still digesting. Okay. Now let's have a look the next one. Okay. Similar way in the okay, so maybe we should go back into here. Yeah, if you want to calculate the height, let's say you know the algorithm how to calculate the height. Now the next thing is to so to sum up from the beginning. Okay, we can determine the packing height of an absorption column if first we know the equilibrium correlation. Yeah, and the equilibrium correlation is actually for dilute solution, and it is usually follow Henry's law. So we should be able to construct the equilibrium curve. But remember, if we because we usually use in solvent-free basis. So for solvent-free basis, use mole ratio, yeah, y versus x. Don't just plot your small x and small y. Okay, you need to change it into mole ratio. Okay. And then the second one is the operating line. Okay, the operating line, as we know it, that it is actually a correlation between the y and the x at a certain height, and it follows this equation, which is L dash h divided by G dash Sx plus this one, yeah, the we can call it the intercept. So if you look at over here, the slope is actually noted with the Ls dash divided by Gs dash. Yeah. So the slope of equilibrium, the slope of operating line is actually defined by the slope between the how much Ls divided by Gs. Okay. Now can we change GS, or is it determined from the problem? Can we change GS, or is it determined from the problem? GS dash. Come on, GS. Do we know GS from the problems, or can we change GS?
Is it given?
Yeah, that's good. It is defined, yeah. But if you have another question, for example, if we want to multiply GS into 2 times, and what about the absorber column, for example, that type of question, of course the GS is changing. So this is defined. So the one that we it can be changed is actually this one, yeah, the LS. So LS can be changed. We can increase LS. If we can lower, it can be we can lower LS. We can increase LS. Yeah. But again, as a chemical engineers, you should think about the consumption, and also it may be related to the operating costs. Yeah. Don't forget. Especially if you're looking at the absorber for, or maybe another column, yeah, the absorber column for many gases, for example MDEA or DEA for absorber, CO2 absorber, it has a cost, yeah, it's not as cheap as water. So if you increase your LS, then you're gonna increase your operating cost as well. Okay, so right, So the common things that we know is that first we know the GS, we know the Y1, we know the Y2, and also we know the input of the X2. Yeah, we know the X2. Okay, because we know the what is the fresh X, yeah, or the solvent. Sometimes because the solvent came from the desorption column, from the regeneration column, sometimes not all of the solvent are removed, yeah, so we still have a little bit of uh, solute there. Now, so similar to distillation column, we should have some minimum slope. Yeah, the minimum slope, let's say this is from y1 to y2, and then this is the slope ls over gs, which define the operating column. We have the minimum slope, and the minimum slope is the one that touch the equilibrium curve, similar to the distillation. Yeah, so this one here is define the minimum ls. Okay, and then again usually we have to find the minimum ls, and then there should be some again an optimum one. Yeah, how many so the ls should be how many ls minimum. Okay, so if the slope touch the equilibrium curve, the height gonna be overall, yeah, because later on then, yeah, this one here, the absorber will not, yeah, it will have a high in infinity height. But so sometimes looks similar to the distillation column. When you want to have the optimum ls, usually it's defined based on the ls minimum, for example 2 times or 3 times and so on. Okay, so this one here, yeah, so at minimum slope ls divided by minimum. Okay, another one, if the slope looks like this, the equilibrium looks like this, again the slope of the operating line that makes its minimum is the one that touch the curve, yeah, similar to distillation column. Okay, and then that is the things, and then the last, I think, right. Okay, so tomorrow I think we can the time is just 10 more minutes, so we can continue tomorrow. Tomorrow so basically to sum up here, just I'm gonna write just very quick here. So to sum up here, we have y. First we know the y1, y2, yeah, the target that we want. We know the x1 as well, and then we have to find also the equilibrium curve. Okay, and then with that we can construct the minimum operating line. Yeah, so here for example, yeah, start from x2 and y2 because we know it, we know also x1, and then try to find the line that has the minimum slope, and this is gonna be your operating line. Yeah, this is gonna be your operating line, the operating line minimum. Okay, once you know the operating line minimum, you will find the ls minimum. Yeah, then you can find your ls minimum. Okay, and then the fourth one, you can find the ls, for example by how many ls minimum from the problems. And once you got that one, and then you need to check the correlation, yeah, correlation between kxa and kya. Find that one then. So then you can construct your graph. Construct your graph to find the which one is y, which one is yi, okay, and then find the function. Find the function, and then you can the third one, the seventh one, you can find calculate the height. Okay, that's the ideal one if we know all of this. Okay, so this is pretty basics. That's why in the exam you have to calculate all of this should be right, yeah, or if not, then you can't pass the exam, then you have to do remedial. I really hope that if you follow the instruction, if you follow the algorithm, and then of course you have to be careful as well, harus teliti, yeah, you should be able to calculate the height. Okay, tomorrow I will explain to you that there's some another term is called gas overall mass transfer coefficient, sometimes with a capital Y. I think it's not enough for today, so we're gonna just put it into tomorrow, and then tomorrow also we'll try for using maybe last year's problems to have a tutorial about this one. Alright, I think that's all for today, and then thank you for